Hey everyone, back with another lecture. So I've been trying to shorten these a little bit. I'm going to tell you up front that this is one that's probably going to be a few minutes longer than the others. A couple reasons for that. One is as we're getting into a section that is very important. I think all these are important, obviously, and all of these, what you all have to understand is we're going through this very quickly, and we're just kind of touching the surface of these things. There are classes taught on just one of these chapters for a whole semester. We're getting into very little detail, but I do want to talk about this chapter a little bit more. This and the next couple. The next one not so much, but the third lesson in this module probably we'll talk about a little bit more. That's because it's about water. And water is basically essential for life on this planet. It is why that we have life here, why this planet is different than others with other factors. So it's very important. Another reason is not only the importance of it, but it's also kind of my wheelhouse. I've told you at the beginning of the semester that my career is in basically water conservation and water quality. I am an environmental scientist, and I work a lot with especially farmers in this area, but with other entities as well, about water quality issues, not polluting the water, how water moves through our environment. So this chapter is right kind of in what I do for my profession. Another thing I'm going to do in this specific lesson, and I think it's kind of important that you do watch most of this lecture video, is I am going to go over karst a little bit. If you remember from an earlier lesson, karst is basically caves and sinkholes and underground drainage of water. And we have that here in our area, in the Bowling Green, Kentucky area. You know, Mammoth Cave is close. And I work with this stuff all the time. And so since we're here and most of us are in this local area, maybe some, I haven't looked really at the roster to see if any of you are at any other technical colleges across the state, but a lot of Kentucky has karst, not just the Bowling Green Mammoth Cave area. So this is kind of a local issue as well, so I'm going to go over some of that as we go through this. So again, this chapter is called Streams and Flooding. So the one thing that I did want to point out too is at the beginning of this chapter we talk about the water cycle. So we're going to talk about that in this chapter and again in chapter 11, which is the third lesson in this module. So we're going to jump around chapters just a little bit to get these things together. But we're going to go over the water cycle in this chapter, and then we'll get into the streams and flooding part of that. So when we talk about streams, okay, so y'all know what a stream and a river is. It's basically water flowing from a higher elevation toward a lower elevation. If you remember a couple of lessons ago, I really put that forward that nature is moving toward its baseline, toward the normal. So I used this example when I was telling you about that. So the baseline for water, where water is that flat surface, is the ocean basically. That's the baseline for all water on Earth because that's what gravity is dictating that water filling the voids up to that ocean level. So whenever we talk about elevation, we say so many feet above sea level. So that sea level is kind of the base elevation for the entire planet. So when we have fresh water moving through the environment, that water is trying to get to that base level, to that ocean. And that's why streams flow downhill, obviously. They're flowing with gravity downhill toward that baseline, toward the ocean. And as they move through the environment, most of the time they're moving in the form of streams or rivers. That's the most predominant surface water type. We also have groundwater, and we're going to talk about that here in just a few minutes as well. But here is a typical stream hydrograph. Now, I told you all that I'm a big whitewater person. I have rafts, I have kayaks, I go whitewatering often during the year. And I use hydrographs all the time because, you know, when I was younger, we didn't really have access to the internet as much. There wasn't as much information out there. So we just kind of had to guess when we would go to whitewater rafting, okay, It rained a couple of days ago, so the river's probably at a decent level, so we'll drive 4 hours and try it out. Now I can get online and I can find these hydrographs from U.S. Geological Survey, and I know exactly what the water level is at any time of any day. I can get on my phone, look it up, boom, I know what the water level is. I know if it's going up and down. So what you're seeing here on this hydrograph is it actually has some information that's very useful to you. The blue line is the level of the water. I say level. Sometimes you can call it a level because a lot of times on this axis over here, it will have a gauge height. Now, because we're humans and we like to have things kind of simple, a lot of these rivers have what they call gauge heights. And that means how high the water is physically in the riverbed. Now, another thing that correlates directly to that, the reason it is that high is because it has a volume that's flowing through it, and that's the stream discharge. So, for instance, when I look at a hydrograph, when I go to a river, I can either look at the gauge height, which is the physical height of the water, or I can look at the discharge, which is in cubic feet per second. So, remember that cubic feet per second, because you're probably going to see that again. That's the measurement that we measure a volume of water flowing past a certain point. So, this line represents that either stream level or discharge, how much water is flowing through that channel at that given time. As you go out this line, that's time. So from this time, this might have been, it doesn't have units on here, this might have been 24 hours ago until now. Or it could have been 7 days ago until now. It just depends on what the units are down here. And then they have on here precipitation events. So let's say it rained during this day. So whenever you get a rain, that water, the runoff, first is going to seep into the ground and become groundwater. Once that ground gets saturated, it's going to start flowing over the top of the ground and make its way into a stream or river, and then that's going to start flowing downstream, obviously. And as that happens, as more area is picked up by that drainage basin, it's going to increase the flow. And that's where you see right here, see the line starts going up really sharply. So if you see a line going up sharply like this, that means this was a pretty intense little rainstorm, and it happened very quickly. And you'll see all of a sudden this little area, this little time frame right here is where the water's still kind of seeping in the ground. It hasn't quite gotten to that gauge yet, and all of a sudden when it starts to rise, it rises quickly. That's called a lag time between precipitation events. Now, when you're in a mountainous terrain, like high elevation, like a lot of the places that I like to whitewater at, that lag time is going to be a lot shorter. When you're in an area like ours, we're down kind of in a flatter area. First of all, the ground can take up more water. It can absorb more water. And since it's flatter, you're going to see a longer lag time for that water to actually get to that stream channel. So in the smaller upland rivers, that lag time is going to be short. The water's going to rise quickly and it's going to drop quickly. Whereas in a bigger river, say the Green River or the Ohio River, you're going to see that lag time a lot longer. And then when the water rises, it takes a lot longer for it to go back down as well because the volume's higher. Because remember, we're moving downstream. And as you move further and further downstream, you gain more and more tributaries. Therefore, you're getting more volume as you go downriver. Again, this is just a diagram of what I basically just explained. You have precipitation. You have some infiltration into the ground. How it infiltrates is going to depend on what type of soil it is, how saturated it already is. If it rained 2 days ago, it's going to be pretty saturated still, so it's going to go ahead and run off faster. If it's like it has been here and been really dry, it's going to really soak up a lot of moisture, and you might not get a lot of overland flow at all from a smaller event. So you have the runoff as overland flow. It mentions plant transpiration. And the groundwater flow. Remember, we're going to talk about the water cycle in detail in this lesson. I have a diagram of it in your lesson. Be sure to study that water cycle diagram because we're going to see more of that in our assignments, on our quiz, on our test. So be sure you study that water cycle. It's going to be very important. So we have what we call drainage networks. So this is just a very simple diagram. We'll say this is the ocean, or it could even be a lake, but we'll just say it's an ocean. And you see the water, the rain, the precipitation will fall into uplands. You see the streams, the tributaries start coming together. As they come together, they get larger as they move downhill. And then eventually they'll get to a flatter area where they'll slow down. And you see the character starts to change in these. You see in the uplands, they're pretty straight. They're kind of linear. They'll form a deeper valley. And as they move down slope, they straighten out a little bit until they get to here, and then you start to see meanders. And we see that here in our area, in the Green River and the Ohio River. You see a lot of meanders. That's because the water is moving much more slowly. It doesn't have velocity. It doesn't cut down as quickly in the valleys as it does down here. You actually have more deposition down here. And I'm going to tell you what deposition is in just a second. So let's go back to this real quick. So these small tributaries, I want to mention, and this is not covered in your textbook, I want to mention stream orders, because I cover that a lot in my job, and it's very important to what we do at my work, identifying stream orders. So it's a very simple concept. So you have these very, very small little tributaries that come together. So each one of these is going to be like a first order stream. When two first order streams come together, you get a second order stream, and so on. So as you go down, two second order streams come together, you get a third order, and so on. So, but if you have like two first order streams, you get a second right here, and you get another first order coming in, it stays a second order stream until two second order streams come together. So by the time you get down here, on this diagram it's pretty simple. You might have a 10th order stream. It might be really large. And this is just an example of that. Two different diagrams here. They're both the same. You can see where you have two ones come together to make a 2. Two ones make a 2. The 2's come together to make a 3. You have a 1 coming in here to the 3, but it stays a 3 because you have to have 2 of the same level to come together to go to the next level, and to a 4, and etc. So that's important for us when we're working in the real world, in the scientific field, because it helps us to identify what type of creek we're talking about. And you can see some little photographs of different ordered streams. You see this would definitely be like a first order stream. Very small, just a very rudimentary runoff. But as two of these come together, you're going to get a little bit bigger stream, maybe like this one. Maybe a little bit smaller than this one. That might be a second. This probably is going to be like third or fourth down here. So you can see how they start to change characteristics as we go up in stream order. Also, I'm going to go back to this diagram. You see this red line at the top of this ridge. That's called a divide. Again, another example of that. This is on a larger mountain. You have a divide. And all that means is the precipitation that falls on this side is flowing this way downhill, and the precipitation on this side is flowing that way downhill. So you might think, well, that's a very simple concept. Why are we even talking about it? Because when you start talking about the big landscape type decisions and problems that we have to know where these waters flow. And where they flow is important to know where the problems may be, how we're going to remediate some things. And here you see some of the major divides on our continent, on North America. So you can see the primary one is going to be right here. That's going through the Rocky Mountains, and it goes all the way from Alaska all the way down through Mexico. What that means is any water that's falling on the west side of this is flowing to the Pacific Ocean this way. Any water, any rain, any snow that's falling on the east side of this is flowing to the Mississippi River and then down to the Gulf of Mexico, which is part of the Atlantic Ocean. So even rain way up here in Montana, when it falls, even though it's closer to the Pacific Ocean geographically as the crow flies, it's running off this way back toward the Mississippi River and eventually into the Gulf of Mexico. So all the water here in Kentucky flows eventually to the Ohio River, to the Mississippi River, down to the Gulf of Mexico is where our watershed is. And when I mention the word watershed, that means a watershed is an area that a specific river drains. So if I say the Green River watershed, That's going to be every tributary that flows into the Green River and all the land that contributes water to those tributaries. And this is an example of watersheds. Now, these are major watersheds, so these are big watersheds. Again, these are watersheds of the Mississippi River. And you can see that example I just gave you. Up into even northern Montana, you have rivers that flow back to the east, eventually to the Mississippi, and eventually back past New Orleans and in the Gulf of Mexico. So you can see, as far as the Mississippi watersheds, these are the major Mississippi watersheds. We are in the Ohio in Kentucky. Pretty much all of it. There's a small little sliver down here that goes into the Tennessee watershed, down near Middlesboro, Kentucky. And then far western Kentucky, it's just considered the upper Mississippi because this water actually flows directly into the Mississippi River. However, just looking at this on my map, and probably hard for you to see it on your device, there's a little orange that's actually not correct. All that should be over here in the Purchase area, not in that part of Kentucky east of the Twin Lakes out there, Barkley and Kentucky, because that water actually flows into the Ohio River and not the Mississippi. So this map's just a tad off, but yeah, we're mostly in the Ohio watershed. If you look at this line right here where my cursor is, that is the Green River that runs right near Bowling Green. The Barren River runs into the Green, so that's all part of the Green River watershed. So I could have a map that's smaller, larger in scale. When we look at Kentucky, we could look at the Green River watershed, the Kentucky River watershed. We can break this down even further than it is now. So just a brief diagram here of a gaining versus a losing stream. A gaining stream is one that actually gains water from the water table. You see the water table is kind of even with it here, but as it goes up the gradient here, the elevation, it's a little higher, so it's flowing in and it's contributing to the flow of the river. Whereas in more arid areas, you have a water table that's lower and the streams are actually losing water flowing downward into the water table that's a little bit deeper. And here's the karst that I mentioned. This is not in your textbook, but we'll see this diagram again. This basically shows you what karst is and how it works. So karst, I've mentioned this before in this class and lectures. We have a soluble rock, bedrock, sedimentary rock called limestone. That is what allows the rock to chemically dissolve along fissures and cracks, and over time those widen and widen as the water moves through those, and they become caves. And those caves flow relatively horizontally because the layers of the limestone are laid horizontally. If you remember from your first lessons, they were made on the bottom of an ocean. So you have horizontal layers of limestone, and that water gets down into those cracks and fissures, starts eroding away chemically that limestone. So as it passes through, as I'm telling you this, of course it's flowing. So if it's flowing, it has to be going out somewhere. In all karst areas, we have a baseline river somewhere. So all this water that you see that's flowing underground is flowing, it's down gradient, even though these bedding planes, they're pretty much horizontal, but they are tilted just slightly. So you have that water going along that tilt just slightly and eventually escaping the hillsides, the river valley, in the form of springs, freshwater springs from the caves that flow into the Green River. The Green River for our area is that base river. It might be a different river. It might be the Kentucky River in the bluegrass area of Kentucky. But you have that base river and all this water is moving toward it. Now on this chart you can also see that you have different cave levels. You have dry cave up here, and down here is the water table that's actively making more cave. So one thing to keep in mind here is at one point in geologic history, remember we're talking about millions of years, this river dictates the water level. So at one time this river was higher in its riverbed. The valley wasn't quite as deep. So what happened was this valley carves out over time and moves downward in its valley. The water table in the hillsides also moves downward and makes new caves flowing into that river. So at one time you had an active wet cave up here. The river table here, the river valley, was actually much higher, and this was the river level. I'm sorry. And as it's eaten down in its valley, the caves have gone down as well. So with regards to flooding, I'm going to mention this really quickly. In some instances, flooding in a karst area is really prevalent. In some cases, it's not. And there's a very simple reason for that. In Bowling Green, on a typical flood, like an average small flood, it doesn't really bother anything. If we have a pretty good flood, a really hard rain, a really sudden rain, and it's really conducive to flooding, we do have some sinkholes that fill up and some roadways that get flooded. And the reason for that, it's twofold. One is these sinkholes have formed and they let water pass through them relatively slowly most of the time. Some of them are more open and they can take a higher volume of water. But sometimes the openings of them are relatively small. So they can only take so much water at once. So sometimes you might see sinkholes out in the countryside. After a really hard rain, they fill up with water and they'll be standing on the surface, and 2 days later it's gone. That's because it quits raining and it filters down more slowly. So that's one reason you might have some flooding in sinkhole areas in karst. It just takes it a little bit longer to filter down a specific sinkhole. Another reason, and a more dangerous way to have it, is it depends on how deep your water table is here. For instance, Bowling Green, the water table, and I forget exactly, I should remember this, but it's been years since I thought about it. It's about 60 feet or so below the surface. So you can see how this water moves very rapidly through these caves, like a surface stream. I mean, it's going in and flowing. In typical aquifers under the ground, it moves very slowly, but in karst, it moves very quickly. So it has, basically, think of a cave as a tunnel, okay? So let's say we have a lot of rain really quickly, and let's say the water table is up here close to the surface. And let's say this cave passageway, it has a certain dimension. I mean, maybe it's 10 feet by 10 feet or 20 feet by 20 feet, whatever it is, it has a capacity. So if we get enough rain quickly enough and that cave passageway fills up with water, suddenly that water has to have somewhere else to go. It's still pulling that water out to the springs, but it's backing up into these sinkholes. And if it backs up enough, it'll spill out of the top of the sinkholes and you get large-scale flooding on the surface. And now that's if the water table is very close to the surface. Like Bowling Green, it's semi-close. It's not like right at it, but like I said, 50, 60 feet down. You can see that water table if you go to Lost River Cave in Bowling Green, out Nashville Road. You can see that very clearly. You can look down at the bottom and you can see where the water table is. There's water flowing in the bottom of the cave. So in Mammoth Cave is the opposite. Mammoth Cave, as you go to Mammoth Cave, you go up in elevation on an escarpment. That water table is 360 feet below the surface at Mammoth Cave. So now, instead of 2 levels of cave, you've got like 5 levels of cave. 4 of those are dry. The 5th level at the bottom is where the water is. So you would have to have a flood that rose that water 360 feet to get to the surface. Now, if we had a flood of that nature, most of Kentucky would be underwater. So, very unlikely that that will ever happen in our lifetimes. However, that's why you don't have as much severe flooding at like Mammoth Cave National Park, is because that water table is so much further below the surface. In Florida, we hear about sinkholes falling in all the time. Their water table is right under their surface. They have a lot of caves, a lot of sinkholes, but there's a lot, the water table is right there, so there's a lot of cave-ins with their sinkholes. Now, back to streams. That's my karst talk for the day. So, stream erosion, you've got, remember we've talked about the different kinds of erosion on rock. It's similar in water. It just exacerbated a little more. You've got physical. You've got chemical to a degree. You've got stream channel migration, which means the sediment in the stream is shifted and it settles in different places. It actually changes the course. You've got things called potholes, which are common in some of my whitewater rivers, in the rocks, the bedrock and or boulders in the stream channel. There's hydraulic action from the water flow, and it creates what's called potholes. Little holes in the rock can be very dangerous in whitewater if you were to get stuck in one of those. And then you've got transportation. Now, the erosion is the moving of material. It's actually breaking off or dissolving material and moving it. Transportation is how that material moves through the water. So Think about when you see a creek after a big rain, it looks muddy, right? It looks like chocolate milk. That is a suspended load. That means there's sediment suspended in that water. So it's moving a lot of little tiny particles with the water itself. A dissolved load, that is when chemical dissolution happens, like we talked about when limestone creates caves, you have a chemical dissolution. That's why we call the Green River, because we have the minerals that chemical dissolution that occurs in that limestone, when it flows in the Green River, it has a green color to it. So you have dissolved load, you've got suspended load, you've got hydraulic sorting, which we're going to talk about that more in just a second on another slide. That has to do with how the individual particles settle out as it's moving downstream. And then you've got the bed load, which is actually the sediment in the bottom. So base level, again, you see here, this would be considered base level for this stream. As you move up in the mountains, it's going to be steeper and higher velocity. So there's going to be a lot more erosion than happening up in the mountains. As it gets down here and it hits kind of a flat area and starts to, you see a meander here. It starts to meander, and you see little gravel bars out here. This is where the river is slowing down and depositing some of that sediment into the riverbed. So that's why you see some of these features in the river where you do. You never see a gravel bar high up in a mountain stream where the water's really flowing fast. That's a depositional type event. So here you have hydraulic sorting. And I prefer you look at this down here a little bit better than this up here. Although this is a cross section, it's a little confusing if you look at this first. But let's say you got a stream running downhill here. And you got all different kinds of sizes of material that are getting eroded away and transported in that water. So typically your bigger rocks, like actual rocks or bigger grains, and especially the more angular ones, they're going to fall out. It takes a lot less slowdown of the water to have those drop out. They don't travel so easily in water. So they'll break off and then they'll settle. As soon as the water starts to slow down at all, they're going to settle out and be on the bottom of the river. That's why when you're in a whitewater river, again, I'll go back to my hobby, in whitewater rivers you have fast flow. So you get that water really rocking down through there. It'll break little pieces of rocks off, and those rocks will follow the bottom, and they're pretty much going to stay there or maybe get carried down just a little bit, and then they're going to settle out. So you're going to have bigger rocks the higher in elevation you go. As you get lower in that stream elevation, as you go, it'll grade down into the smaller and smaller and smaller sediment until the very end you're going to have the smallest, like sandy or smaller grained sediment at the very end. Like a soil clay type sediment is going to be found further down. So you'll go from rocks to pebbles to sand to clay to silt, all the way down. You're going to change where those things are falling out. That's called hydraulic sorting. That's why you see different kinds of gravel and different types of streams depending on how far up and or down that is in the stream channel. Here's those potholes I told you about. You get some hydraulics forming here, and they just kind of skewer out a little hole, and it's kind of like a washing machine motion right here. Very dangerous for us whitewater people to get in one of those. Let me see. So here we're going back to what I mentioned earlier about the deposition. So you got active erosion going on when you're coming down a stream. You see there's a curve here. So as a river goes around a curve or a meander, the highest velocity is on the outside of the stream. So you're going around the curve, and that high velocity is going to eat away at this bank over here. It's going to eat away at the dirt, at the rock, whatever's there. The inside of that curve is lower velocity. So a lot of times you're going to have sediment settling out on the inside but not on the outside. So that's why you have gravel bars and stuff. If you go on canoe trips a lot or anything around here, you'll notice most of the gravel or sandbars that you see are on the inside of a curve, not the outside, on the inside. And you can see here how it's kind of eating away at this bank. It'll fall in and eventually settle in on the inside. So these are just a few diagrams to kind of show that. You get the same action in river deltas. A river delta is where a stream actually exits its channel, flows into a lake or the ocean, and you're going to see a lot of deposition on a river delta. Again, these are just two photographs. This is going to be more your standard high velocity, early order type stream up in the mountains. You see all the big boulders and big rocks settling out up here. As it flows down, it's going to eventually flatten out at some point, maybe 100 miles later. You're going to be in a flatter area. You can see how it starts to meander, and you can see the gravel bars, the depositional bars that form on the inside of these meanders. A delta, I just mentioned, this is where the water actually flows out of a river into the ocean. So when you get out of the channel, you have zero velocity in your river, right? So all the finest sediment is going to immediately settle out here and form what we call a delta. It's actually growing the land. And if you look, New Orleans is right here. This is the Mississippi River Delta. You have a huge delta area here with a lot of deposition. And that can cause problems because human activity, like farming especially, we cause a lot of erosion when we farm and we cut trees down and we clear land and we farm. We cause a lot of erosion. So this has, in the last 200 to 300 years since Caucasian people have settled the United States, stuff like this has mushroomed in size as far as how much sediment is actually flowing through this system and creating new land down here in the river delta. Now, when I say new land, it's not really usable land like we can go build houses on or anything, but it's building up and building up. In addition to that, I'm just going to mention this now, and we'll come back to this in a later lesson. With that sediment comes a lot of chemical runoff, and that's creating a huge dead zone out here in the Gulf of Mexico called the Gulf Hypoxia Zone, and I'm going to talk about that later, but that's another very, very serious issue that I work on a little bit here in Kentucky because we're one of the states that are included in that the Mississippi Basin, about the killing of the aquatic environment because of the farming chemicals that are going down and going out the Mississippi River. Alluvial fans, now these are going to be a little bit similar to deltas, just these occur typically in a higher elevation, and you can see how that all that material that's eroded here has flowed down these little small channels, and it's just being dispersed down here and deposited because the velocity has changed. And this is just characterizing the rivers and streams when it does kind of slow down and get to closer to this base level. Here in Kentucky, we're going to see a lot of this kind of thing. You'll see your floodplain. The floodplain is a very unscientific definition of a floodplain is basically where it's pretty common for floods, the water level to get up to a certain point. There's usually a small little escarpment type bank that's going to differentiate your floodplain. So the base level is going to be here, but the floodplain level might be up several feet in elevation. For that, because when that stream starts to build in volume, it's going to spread out. You can see over time it's going to widen, and within that floodplain you're going to see those meanders start to happen. So you're going to get extensive erosion over here and over here when that happens. And these are just some, I'm not going to go through these in great detail right now because this is going to be a long lecture and you have these in your textbook. Natural levees and back swamps. I'm just going to mention this because these are covered in your textbook as well. These type of environments that you see here in the back swamps and behind these levees, these are very important for nature to control their own floods. These areas, if we leave these natural, it really helps in flood mitigation for human purposes, for destruction of homes, for damage caused by floods. When we come in here and we rip these things out, take out all the vegetation, this is no longer protected. The root systems protect these areas, and just the plants being there slow down the velocity. You can see here you have high velocity in the channel, but you have relatively low velocity out here when the flood happens. Even if the water gets up in there, there's not a lot of damage done because of all the plants in place. When we take all that away, we have huge amounts of erosion. People tend to want to live in these places, or at least farm these places, and that's when we have catastrophic damage because we shouldn't be taking these environments away from riverbanks. And we see that a lot here in Kentucky. Again, these are some things that are in textbook. I'm not going to go over these in detail in this lecture, but this is just a little bit more scientific with regards to flooding and how floods can harm. We can see the flood plain here. You can see a home constructed here. You can see how that home is in great danger, because if this flood gets high enough that it's going to jump this natural levee, it's going to completely flood these entire areas to the side of the river. And this is, again, this is how we measure velocity and or volume, discharge, cubic feet per second discharge. And you can see that measure right here. This is just how we measure it. I did this a lot in graduate school. You can calculate like this. We actually went out and did it by hand a lot. We have measuring tools that we go out in the river and actually wade in the river and determine that. Discharge versus recurrence interval. So I'm not going to go through this in great detail, but what I'm going to tell you is I want you to know a little bit about this from your textbook. You have recurrence interval in years, percent probability. These kind of go hand in hand. These are kind of synonymous, because as you see, maybe you have a 10% chance to have a flood. That would be a 10-year flood. If you have a 1% chance to have a flood like that, we call it a 100-year flood. We could expect that once every 100 years. If you have 0.1% chance to have a flood, that's a 1,000-year flood. And this is a chart that shows these things. And this is the discharge on this particular water body. So what I want you to get out of this, though, is a real-world kind of example. And what I mean by that is we're hearing a lot about climate change right now. And we hear about these floods happening with more frequency. We talk about that a lot. And you might wonder, well, what's that mean? Well, what that means is when we have these recurring floods, we can expect a really bad flood, let's say a 1,000-year flood. So we have a 0.1% chance to have a 1,000-year flood any given year. Okay? Well, that is calculated through a geologic record that's been studied over the years, and what we can delineate from past floods and since records have been recorded. And we can get these percentages and when these floods can occur, okay? So climate change has changed our precipitation patterns greatly. And me being as old as I am, I can see that in my lifetime. You know, when I was young, we used to get more rains that were like constant, maybe 2 or 3 day rains, but gentle rains. You know, it just rained. It wasn't like a flooding rain. It wasn't real hard. It just kind of rained for a couple days. We had our storms too. Don't get me wrong. We had that as well. But it was kind of equal between the two. Now, it seems like every other rain is a big flood event. Like it just dumps like 2 or 3 inches a day on us. That's become much more common in today's world than we saw back even when I was young. And now you hear on the news, they might say, well, we had a 1,000-year flood. Well, now we used to have, a 1,000-year flood means there's a chance to have that every 1,000 years. Well, now we might have, on average, 3 or 4 or 5 100-year floods in a 6-month period. That's not unheard of anymore. So as we go forward, it's kind of changing the averages in what we call a 100-year flood, but they're happening with much more frequency than they should based on historical record. So that's why when you hear, okay, that we've had 3 100-year floods this year, well, that's exceptional because we shouldn't have more than one. We shouldn't have more than one every 100 years, but it's happening more and more frequently. And there's a lot of data that supports all this stuff. It's not just people talking and saying, oh, it seems like, I just did that. I just did an analogy that's very unscientific. I said, well, I noticed this when I was younger. That's a personal observation. There's also data like this chart that we can plot these things and we can say, yes, we had X number of 100-year floods last year in this specific area. The one that we just had in Eastern Kentucky a few months ago was exceptional. So these things are increasing with frequency as we go forward, as climate change really is changing what we're seeing in the natural environment. So again, with everything we've talked about, what really affects how bad a flood is? Well, you have the precipitation, how fast is it, how hard does it rain, how much snow do we get and how fast does it melt? That might be an issue, maybe in the mountains somewhere. And then you have what kind of soil do we have? What's the saturation of that soil? Has it been raining a lot the last month? Has it been really dry? How fast is this water going to be running off and getting into rivers and streams? And then what's it going to encounter once it gets there? And then another factor is, what's this watershed like? Do we have half the people living on a riverbank? Is our land cleared for farming? That also plays a role in how bad a flood is. What we've done to those areas. Types of floods, we got flash floods, which are very quick floods. I'll let you read about those. I think you probably know what those are. Just keep this in mind on this slide. So sometimes it's not as obvious, and I experienced this some in whitewater. When we're paddling, you see this a lot in desert areas out in the west when they have flash floods. Depending on the watershed, you might have say you have a severe thunderstorm way up in the headwaters. It might be miles away from you. You might be down here on the river somewhere. And you might have a storm miles away. You might not even know it rained up there. But say they get a 100-year flood up here in like 2 hours. And you're down here in a kayak or canoe going down this river. So eventually all this water is going to fall here and it's going to make its way down these streams. Eventually it's going to hit down here somewhere. And it can be very dangerous for the people on this river down here. Now, I just mentioned if you're kayaking or in a canoe or something, of course that would be dangerous. It can also be dangerous if there's a small town or a house on the side of this river and all of a sudden this big flush of water comes down all at once. That would be a flash flood. Now, when you have flood events, this is a good chart right here to show you what I showed you before. A rain event in the headwaters. So if you look at the hydrograph at these different spots right here, you're going to see different things for the same rain event. Remember I told you up in the mountains where the streams are smaller, the water runs off really fast. So you're going to have a really steep spike real fast and it's go right back down. Whereas if you're down here, maybe this covered more of an area, you're going to have a slower initial curve and it's going to go down a little slower because that water keeps running down until it finally goes away. All the way down here at the bottom, it's going to be a more smooth curve and it's going to be further out in time. So this might be the same day. This might be a day or two later by the time it gets down to sea. So floods can happen in a variety of different ways and in a variety of different locations depending on where that precipitation event is and what type of watershed you're in. And I've already touched on this, how human activity really, really hurts us with regards to flooding. Flooding would not be near as destructive as if we hadn't destroyed landscapes basically around these rivers. And if you notice, most populations live near a water body, so we've really affected rivers across this entire nation. Y'all saw just a few weeks ago, probably a couple months ago now, the Yellowstone. Out in Yellowstone, they had the massive flooding out there that took out all the roads into the park. Similar situation to this. That was probably a 1,000-year flood that they had out there. I have to look that up to see exactly what it was, but it was a very large flood, very rare. And here are some of the solutions that we can do for our purposes. It says we could put dams on rivers. Now that's a good thing and a bad thing. We're going to talk about that more in just a second. Dams can control water release, but they also do a lot of damage to the environment and can make things worse if they're not managed properly. Artificial levees, channelization, erosion controls, all these things, again, they're engineering solutions for humans. They're good in the case of helping populations like a city that cannot really pick up and move. So we have to have engineering solutions for those areas. But the best ways to avert flooding and catastrophe with flooding is basically returning to nature, restoring wetlands, efficiently managing our floodplains, educating people on that. That's the best foolproof way to control these floods. This is just a brief visual for New Orleans. Remember Katrina, or maybe y'all are too young to remember Katrina. When you get as old as I am, you really don't have a concept of how long ago something was. I guess that was several years ago now. but basically the whole city flooded in a hurricane. And you can see here why. You see that New Orleans is actually a little bit below sea level. Part of it is, not all of it, part of it is. You can see how this is the Mississippi River. That's the level of the Mississippi. This is Lake Pontchartrain, which is on the north side of New Orleans. And they're sandwiched in between two water bodies that they have levees built, but if these levees fail or the water gets too high, it's going to flood everything, and that's what happened during Hurricane Katrina. A city like New Orleans, I mean, there's no really good answer, even with engineering. There are just some natural disasters that they're not going to be able to overcome. And you might ask, okay, why is this so low? Because remember a few slides ago, I mentioned the deposition that happens at the deltas of rivers. Well, since New Orleans was built a couple hundred years ago, probably 200-300 years ago now, they've built these levees. There's no longer any deposition of sediment. So the sediment in here are staying the same or actually going down. It's sinking because dirt over time compresses. And especially with the weight of all the buildings and infrastructure, it's compressing the dirt and it's actually sinking a little bit. And there's no recharge of sediment because the river has been cut off from flowing through here. And this shows you how this is the delta, how that sediment flows out from the land. There's still channels under the water, but it's basically hardly moving at all. So all that sediment that's being carried deposits out around these channels, and that's where you're getting the land building. Again, Hurricane Katrina, this is what it looked like before and after. There was a levee right here. It breached, and the whole city pretty much flooded. Sediment pollution, this is one of the things I address with farmers all the time. We try to keep sediment from getting into the water. Now, as you've seen, some sediment is healthy for rivers because it builds up. It's part of the natural process. However, if you take humanity away, the amount of sediment getting into rivers is much less. You can see the examples here, how we disturb land, no vegetation. See how milky this water is, muddy coming in here. We put a lot more sediment into rivers than we did prior to human development. So that really, really smothers out a lot of the ecosystems in rivers. They're made to take some sediment, but not the amounts that we see today. And in addition, some sediment carries some of the pollution that we have with regards to nutrients from farming, and we're trying to keep that from happening as well. So sediment from farming, sediment from construction projects, everything is negative to the environment with regards to sedimentation from human activities. Again, we have wetlands. Some wetlands are in river bottoms, some are upland wetlands. Very important because they store water. During a flood event, water is going to be stored in these areas and not run directly off into the river. When you have urbanization, like you see here, all the water that used to seep into the ground in these wetlands, it hits concrete and flows right into the river very quickly. Therefore, there's nothing to stop it. It's just so fast. And you see here a hydrograph with the same rain event, but this is what the hydrograph looks like urbanized because it's just running off concrete. You see how steep that curve is. It goes right up because all the water is going in immediately. Versus natural vegetation, some of it's seeping into the ground. There's a lag time there, and then less of the water actually gets into the channel of the river. Dams, I'm not going to talk a lot about dams. Again, there are a way to kind of help flooding in some circumstances, but if we don't manage them properly, they can be a disaster as well, especially if they fail. And they are not very good for the environment as far as our ecosystems, but they do have their place in some circumstances. Artificial levees, again, we have levees, or basically they're walls or earthen walls built up to keep water bodies in their channels to go around a city. Instead of flowing out into the city, they'll let the water go past the city. Now, that's good for the city. But one effect that you have here is, and again, this goes back to my whitewater, when you have a large volume of water getting constricted down to a very small space, what are you doing? You're speeding up that velocity tremendously right through here. So while these levees are saving this city, and that's good for them, What do you think's happening downstream of this levee? The water has sped up, it's eroding more, and it's going to cause a lot more problems once it passes by this city. So as you can see, even though there are solutions to problems in certain areas, a lot of times those solutions cause problems in other areas. Sometimes levees can fail. You see one here. This is along, I remember seeing this, I'm pretty sure this is along the Mississippi River, or at least one of its major tributaries. This was a levee right here. You see it breached, and there's a secondary one here. They breached, and the river got over into the floodplain. So now everything in this whole floodplain is flooded, and likely we're only seeing a small part of this. There's a huge floodplain, probably has farms, houses in it. Now it's all flooded. So again, you can channelize rivers, and again, you know, this looks great, looks nice, neat, straight, right? But here you have natural processes happening. Nature's kind of taking care of itself. It's meandering. As it meanders, it slows itself down, deposits. Here you straighten. Now that might help the people immediately around this, but you're increasing velocity. And as when you increase velocity, you increase erosion downstream. So you have to look at a very big picture when you do these things, and not just the immediate area. Retention basins, these are basically, think of like almost a small lake, but it really doesn't have a retention feature. You can close it off or open it up, and that way when, say, a lot of water is flowing into this area, you can see this looks like here, and I'm just guessing, but this looks like where the water would leave, the spillway area, or maybe that's an entry, maybe this, like, let me take that back. This is probably coming in from another drain behind these structures, and this is probably where the water actually spills out and carries on downstream, because that looks like a box that would, once the water gets up to that level, it's going to flow into that box and flow out into a channel. So these can be helpful, especially on a smaller scale, because this is not that big, so you're not draining a large area here. As long as this box functions properly, it should evacuate that water. So a small scale, something like this is pretty good. Zoning, just don't let people build in a floodplain. That's a very, very, very simple solution. And one of the last slides here is, and this is something about my whitewater, and you should hear on the news all the time, water is very dangerous in a flood situation. Just a little bit of water, a foot deep, can be dangerous enough to start moving a car sideways. 2 feet deep, it can completely move a car sideways. So we have to be very vigilant as far as if you ever find yourself in a flood, be aware of the dangers, and you need to take the proper precautions. One of the biggest causes of death in whitewater in my sport, in the commercial sense, is when people fall out of a raft, especially on commercial trips, because they don't know any better. And the water's not that deep, maybe up to their waist, and they try to stand up in that water and it's moving really fast, and they get their foot caught in a rock. And they don't realize it at the time, but once they got caught, that water kind of lays them down, and they're not strong enough to get back up because the water's so powerful, so much force. So be really careful when you're in moving water. It might not seem like a big deal, and it might be fine, but it might not. You really don't ever know. So that's going to conclude our lecture. I'm sorry this was so long. I know that's a lot, but there's a lot of good information in here, and this is going to save us a little time on our lecture. 2 chapters from now on water, your water resources, we're going to talk about some of the same kind of stuff in there, but a little different scope. And just let me know if anything. Thank you.